Welcome to today's seminar. We're going to focus on basic concepts in reinforcement learning, and then we're going to end it by creating a very, very simple Q-learning agent to play a game of smart cap. Okay. So I know that you'll already have an understanding because we've been working on the obstacle tower challenge. So I won't go into the very, very basics, but the first thing to understand is what the difference is between supervised, unsupervised, and reinforcement learning. So can anyone tell me what the difference would be between supervised and reinforcement?
So for supervised, you know the output,
Right.
set of outputs, but in reinforcement, you do not have outputs.
So you have outputs. Anything else?
In both supervised and unsupervised kind of classification, they do classification task where you have target, but in reinforcement there is not. It's not classification. It's about setting or working on a goal.
So in that case, can you model your reinforcement goal to be a classification problem? For example, given a state, so state, okay, classify the action. Is that possible?
It could be, but there will not be that many action, that many class. I mean, in case of supervised and unsupervised, there is a limited number of class. But in case of reinforcement learning, you can take any kind of action. So it is kind of good.
I would say that also depends on the problem, because say for example, even in pretty complex games like the obstacle tower challenge, you have very limited actions that you can do. You can go forward, backward, left, right, and maybe rotate, and that's about it. So your number of tasks is still quite limited.
In reinforcement, you're just not telling it exactly what to do, but you're just kind of supporting it by giving it more reward every time it goes in the right direction.
Yes, that's right. That's what reinforcement is. So one more distinguishing factor here is that whatever actions you take in reinforcement learning, it affects the environment.
Yeah.
Okay, in a normal classification problem, say supervised learning, if at this point I'm classifying an image as a cat, okay, and that's the correct label, no matter what I do, tomorrow I will do the same thing. Right?
Basically, the concept of reward and punishment will come in reinforcement learning.
Yeah, that's right. Okay, and one more thing, the thing about modeling it as a classification problem, it basically will not really work because, say for example, something like ImageNet has 10 raised to 6 classes, sorry, not classes, images, and it takes about a day to train with state-of-the-art algorithms. But if you take AlphaGo, that has somewhere around 8 into 10 raised to 100 possible states. And to train this, like telling it in a classification problem, basically, so one magnitude larger would take maybe 1 day longer to train.
What does it mean when you say one magnitude larger?
So ImageNet is 10 raised to 6, right? 10 raised to 7 would be 1 magnitude larger, right? 10 raised to 8 is 2 magnitude. But 2 magnitudes larger would become like 10 days. 3 magnitudes would become 100 days. So it's exponential difference. Okay, and so just examples of what we do here is supervised is the normal classification problem, unsupervised is clustering or something like topic modeling. Okay, And reinforcement learning would be something more dynamic, like training an agent to move through a maze, or it's more like a humanoid task.
When you said the action also affects the environment and reinforcement, can you elaborate a little bit on that?
So say for example, you're in, let's say a maze. Okay, say not really a maze, but a simple thing where you're an agent here. You have to collect some things to get rewards, and there's an enemy in the maze, right? So suppose you move here, and you move back. The enemy also moves, right? So now, based on where the enemy is, you may decide a different action, even though you're on the same state over here.
Can we call a reinforcement learning somewhat like a hierarchical, where it combines parts of supervised learning and unsupervised learning?
You could combine parts of supervised, but it's kind of like a different concept altogether. I don't think you would use unsupervised here, right?
So, can you write the question?
Okay. Paul, when you say the change of the environment is specific to the agent only, right?
Yeah.
Not with the overall environment, right?
I mean, every action you take affects the current state of the environment. So,
With respect to the agent, right? Because
when you say with respect to the agent, what do you mean?
I mean, like, let's say I'm here, I can see this one, right? But once I move here, I just see this environment. For me, there is a change of environment. That's what I meant.
No, but you could also think about it that just because you can't see it does not mean things are not happening behind you.
Yeah, that's my point. So the change of the environment is only is related with the agent.
Not necessarily, no.
Because the overall environment remains the same.
No. In the same example, suppose I've turned my back and the enemy is behind me. If I do something here, that still changes at the back, right?
So, Sanas, I never heard of the hierarchical combination of something. So, can you explain what is a hierarchical combination?
So, if you take the world model, for example, we have parts. Hierarchical combination would be like
World model is too complex.
Okay.
Something easier.
easier. Okay.
So I never heard of the hierarchical. I don't understand what is a hierarchical combination.
It's just a fancy way of saying you combine the two techniques as a subpart.
So you can remove the hierarchical part safely, right?
Yeah, a combination.
So, okay, then let's do not use
Yeah.
fancy word, not knowing what it really means.
Yeah.
So it's important. We should be modest. Try to say, don't make the fancy words and guess things. Don't expect it looks us how somehow better than we know. It actually makes us very very ignorant.
Okay.
Yeah, so we should be careful when we express. So Paul started with simple supervised learning, SL, unsupervised learning, and put the RL in between, right? So this is a very common way of introducing RL. It looks like it creates more confusion
Yeah.
than it was. The reason is you guys are not familiar with what is SL or UL. The reason why we could not start easily was because we did not know the basics. Because we don't have the foundation, something that is supposed to be easy introductory comment becomes a complex thing. So we should reinforce our basis further before we too late. We are graduate level, first year graduate level, and we should know better than this. So, okay, so what is the supervised learning? What is the definition of the supervised learning and unsupervised learning? Can anybody say?
You have label data and supervised learning.
Label. So label is we can call it ground truth. So we know whenever there is a input, we know correct output, right? How about unsupervised learning?
The output is not given.
So output is not given. The ground truth is not given, right? So why people try to reinforce more learning between SL and UL? Can anybody guess?
Because you're still trying to direct the kind of direction in which the agent is going in reinforcement learning by
So
giving it
Aishwarya, so yeah, can you say it again?
because it's you're somewhat supervising it by giving it what's not supervising might not be the right word, but you're still giving it a sort of direction.
So you are almost there, but your
Ground truth
expression
exists.
is ambiguous. You should specify what is the you think more about how you can make it more concrete, right? And Sanas?
So ground truth exists in case of reinforcement learning.
Exist.
But you're not necessarily trying to have a rigid direction. Like you want the algorithm to naturally find its stumble up or through random action find its way to.
Too complex. Too
Okay,
complex.
okay.
Yeah, it is not too that complex. You think in more concrete terms. Aishwarya, do you have any idea?
You're giving it a specific environment within which an agent should
You can forget about the environment thing. Totally remove the environment thing for this diagram. When we talk about SL and UL and put RL in the middle, we don't need to think about the environment.
Can I say, or can you say that we're rewarding and punishing?
Rewarding and punishing is you can say think of it as a ground truth, right?
It's trying to maximize a particular value.
Everything
we're
is maximizing. So
It is trying to learn the inputs which will make it reach the ground.
no. So you guys are overthinking. When you understand something, it becomes very simple, right? So in the context of the SL, every action has a ground truth. So let's say you build a robot. It does the Atari game, right? In Atari game, there is a situation. You may go left, right, shoot laser, missile. For every action, the system says, "Oh, good." "Oh, bad move." Right? For every action, it gives you, "Oh, good, bad, good, bad, good, bad." So if you have a ground truth or label for every action, you have a supervised learning, basically, right? And in unsupervised learning, you do not get any feedback. Whatever action you do, the system does not say anything, right? The reason why we put RL in the middle is that the RL problem is structured such that for sequence of the action, it gives you ground truth. Because it is not ground truth, we call it more of the reward, or positive or negative, or score. So if we do supervised learning, every action should have the score. Oh, you did a 5-point movement. But in reinforcement learning, you are given the reward only
At the end,
After a few set of actions.
after a few set of action,
After significant set of actions.
sparse. So
Sequence of action.
So you get very sparse reward, sparse feedback, right? So why this creates a unique problem? Because you get reward at some point, but you do not know which of this action was actually good action or which was bad action, right? If you are playing an Atari game, maybe you did some bad action, but after some bad action, if you do good action, you get the point, still get the score, right? So for reinforcement learning, because the ground truth is sparse, you have a credit assignment problem. Credit assignment problem is, I got some score or reward, but I do not know which of this sequence of action was helpful or not. So in that sense, the RL is in the ground. Shade, can you repeat what I said? So when we say RL is in the middle of the SL and UL, what do we exactly mean?
so it means that we have some ground truth,
Mm-hmm.
but it's not for every action.
Mm-hmm.
So we get the reward at the end of some actions.
Mm-hmm.
So the reward is basically sparse.
Mm-hmm.
So that's why it stands between these two.
Mm-hmm. Okay, that's very good. So we had some talk of the environment. So how we can think the robot action or Atari game as a classification problem. So how we can frame that? So let's think about the shooting game. Shooting game has a state, right? Like enemies are in front of you, there is a missile here, things like that. So if we can think of the Atari games, let's say Atari game had an 8-bit register, then how many states we have? We have 2 to the 8 state. Do you understand what this means? Aishwarya, do you understand what? So it means Atari is a game machine, right? It has a register. What does register means? Register state stores the state, right? So the game state, like the enemy is here, the missile is here, things like that, should be stored in the register. If we copy the register and turn off the machine and repopulate the register, then we get the exactly same state,
Okay.
right? So if it has an 8-bit register, it means that the system has only 2 to the 8 possible state, right?
So it basically means you mean binary. It could be binary states. That means whether agent is on the corner or middle.
So I think Atari does not have an 8-bit register. It has a more than 8-bit register. But anyway, let's say you build the game, you have to store the state, like where the enemy is in some, you said binary, but you can use the 3-bit to create a number, right? So it does not have to be a binary. In what I was trying to say is that the Atari game machine has actually very limited state compared to the modern computer. How many bytes do I have to store to turn off to save the current state and then turn on and load it, and I have the exactly same state? How many bytes do I need? Shadek?
For 8-bit, it's just 1 byte.
For modern computer, let's say you have your laptop.
Okay.
You want to turn it off, right? But you want to save it somewhere. And after you load it, you should have the exactly same state.
In modern computer, I guess 2-3 gigabyte. I mean, our laptop, 2-3 gigabyte of memory is needed to store.
So, have you taken the computer architecture course? No, okay. So RAM is only the part of the game. There is a thing called architecture. Register. How many people understand what I mean? The register thing.
I understand the
You
register.
understand? Yeah. So if you have taken the CPU architecture, memory is one thing, but you need things like for example, program counter. How many people knows program counter? Program counter? No? Okay. So we need this kind of information to fully restore the state, right? If you store all the memory, or if you do not know where the machine was reading at the time, you cannot perfectly restore it, right?
Yeah.
So anyway, so in terms of the Atari game, it has a very few registers, so the state is not so many. So for every state, like a state 1, let's say we can have up to 4 action, like up, down, left, right? Then for this state, which one of these 4 action is the right action? That is the
The policy.
Yeah, this is basically classification problem, right?
Mm-hmm.
Given image, which object are in the this image is the same problem. So that was one point Paul was trying to explain. So let's go. Any other questions?
So one last thing to mention is that in supervised learning, you are maximizing the current inputs. You're trying to reduce the loss on just the current input. And in reinforcement learning, you're basically trying to maximize the future reward that you could get, right? Okay. So a couple of other basic things is there's something called a value function. Okay. It basically tells you like it gives you a value of how good it is to be in that state. Okay, so it's represented by V of S is going to be the expected. This stands for the discounted future rewards.
What is discounted?
So why we discount them is, say for example, I'm running through a very complex maze, okay, and at each step I may get some reward, right? It becomes very difficult to predict future rewards, right? So say I do one action right now and I do that same action say much later, okay, even though it's the same action, I may have collected a small coin, okay. Since it becomes difficult to predict that same thing in the future, you discount it.
What is
Okay.
difficult to predict?
So it's difficult to predict the future, right? Because say 10 time steps from now,
Future in terms of reward or in terms of environment?
both. You don't know if the coin could still be there, so the environment, as well as whether you would be able to reach it, right? There could be an enemy in the way, there could be different things. Okay, so this is discounted future reward given that you are in state say S. Okay, how we discount it is we have so g of t normally would be say the reward at t plus 1 plus the reward at t plus 2 plus the reward at t plus 3 and so on. So this becomes so when you're discounting it, you basically multiply it by gamma raised to k. Okay, gamma is a hyperparameter, so in this case it will be gamma into reward at t plus 2 plus gamma squared reward at t plus 3. Okay, so that's the value function. So it tells you the expected cumulative reward at a particular state. Okay, so given this state S, what is the expected cumulative reward?
So it's saying that given that I'm in this particular state and
Yeah.
I continue like this, this is the kind of reward that is expected. So,
Yeah. Okay. Now then there's something called a Q value. So this has one more parameter in the function. Okay, so this maps the state and the action. Okay, so it's basically telling you the expected reward given that you're in state S and you take a particular action, right? So the difference between these two is this is for all actions, this is for just one action. Okay, and right, so basically what you could say is this could be represented as the max, okay, for over all the actions of V of S.
I do not understand. So, what is the output of the Q value? So
The Q value is basically the expected reward given that you're in state S and you take action A.
Mm-hmm.
And the value function is just the expected cumulative reward given that you're in state S.
Mm-hmm.
So this basically, the representation is,
Oh, I do not understand the max A part.
so it basically from V,
Mm-hmm.
right, you, since it's cumulative of all the actions that you could take,
Mm-hmm.
you take the best action.
No, can you give me a concrete example? Very
Okay, so-
simple example.
So very simple example,
Mhm.
if you take Q learning, you have a structure for each state and each action. So in your Q table, you'll have a table like this, and for each action, you'll have some sort of value, right? So say the goodness is between say 1 or 2 or minus 0.5, something like that, right?
And this goodness is the cumulative of the
Yeah.
expected rewards.
Correct. Okay, and so the value function will be this whole thing, and your Q function is going to give you the best action, so it will be just this, the maximum value.
So as the number of actions increase, the Q function becomes better.
Correct. No, not better. I mean, it becomes bigger. Yeah.
Bigger.
I'm sorry, I still cannot get it. Can you explain more concrete? Do you have a very simple example?
Simpler than this. Maybe I'll think of something and get back to you.
And one thing, like how do you determine the values 1, 2, minus 1?
This is just random right now. We're going through how
There is
the
a
algorithm
mechanism.
works. Yeah.
So let's say there are 5 action,
Right.
then there will be a 5 column.
Yeah.
And if I say I do the first action, then should we give you the one,
Right.
right?
Yeah.
Then why there is a max A vs? What is the max A means?
Max A over here means the maximum value over all actions A.
So
For a particular state.
Yeah, for a particular state.
Yeah, I think I have one input that I could add. So
Mhm.
I read about these two concepts called exploration and exploitation.
Mhm.
So exploration is when the agent randomly performs different actions.
Mhm.
And when it performs action 1, it takes into account what reward it's getting.
Mhm.
Similarly, action 1, action 2, action 3. And then it develops a sort of understanding of what reward it's getting for each action.
Mhm.
That is when it forms that table.
Table.
Mhm.
And exploitation is when it chooses a maximum reward. When it chooses an action associated with the maximum reward and performs that action in order to maximize its reward.
Mhm.
The Q value is used for policy making, right?
Yes, it's determining what action to take.
Yeah, so that
yeah.
it's used for policy.
I don't get the maximum part. So should it be average? What I mean by maximum is if I understand correctly, let's say maximum clear. So please correct me if I'm wrong. Let's say state 1, 2, 3, 4, 5, action A, B, C, D, E.
Yeah.
Right? So, and I want to find the Q1, comma B. Right. Then you are basically saying max A was B, VS. Right? VS is this. Am I right?
B1.
A equal
Yes.
Action was B. Action was B. And let's say
Okay, can I just say one more thing? So this is just the relationship between the two. Okay.
between Q and
Yeah.
B. Yeah.
Alright. If I actually want to get the expected reward, I will just look up the table with these two values.
Yes. So
So 1B.
So if you
it sounds like if I took the action B,
then we're
then
not doing any max, we're directly looking up the table.
it gives you V of S when action was B. Right?
Right.
So the reason why I cannot get the max part is, please correct me, I think I'm wrong. It sounds like if you chose B, what is the maximum reward possible?
No.
And it sounds reasonably, I think, what is the average reward possible? So I think my question
correct.
is...
So what you're saying is correct if you just look at the Q function, right? So now think of it. This step that I've put over here is only the relationship between the Q function and the value function. Okay. It does not mean that when I put the parameters S and A, I'm going to do a max of this. So if you take the same example,
So Paul, when you after this seminar, please check the
I'll clear it up. Yeah.
mathematical formula. I think there is some
Slight difference.
some minute mathematical notation. So
Okay.
yeah, I think
Sure.
yeah.
Okay. Let's go ahead. Okay. So then we come to what's called the Bellman equation. Okay. Sorry. This is PT plus 1. So the Bellman's equation was basically introduced in dynamic program. It was a concept where they broke down a very, very complex sequential problem into smaller time steps to make it a series of smaller problems. Okay. So what it does here is you're trying to get the expected reward of the next. So when you take an action, the reward that you get plus the discounted expected from the next step.
Starting from that state.
Right. And this is given that you're in state S.
So Paul, what is the difference between Q S comma A and V S comma A?
Sorry. This should be Q. In the original Bellman's equation, they actually used this notation for V. In reinforcement learning, this is going to be Q, and this is going to be Q of S, comma, given the action A.
Okay.
Okay. So there are two main methods that we use in reinforcement learning. One is called Monte Carlo, and one is temporal difference. Okay. In Monte Carlo, what happens is you do not update at each time step, but you play a whole episode and then update the value of Q value functions going backwards. Okay.
For
So
the intermediate axis.
yeah, you do it for all the actions, but you do it only after you complete a whole episode. Okay. So in Monte Carlo,
is the end.
Correct. Normally in a game, it's the end of the game. So if you see the difference over here, okay, g of t here is the expected discounted reward, right? So when you play the whole episode, you already have the actual reward that you got in that sequence, right? Whereas here, what you're doing is, this is the your prediction. So from your current table, what your prediction is. So you've got, when you took that initial action, the reward that you just got, which is the reward at t plus 1, plus the expected discounted reward.
Can you check the Monte Carlo formula again? There should be some kind of VST plus 1.
No, because that is represented by this.
No. Then if you look at I'm just checking the mathematical formula. You are saying VST
Yeah.
is given by VST plus something. So
Correct.
you are basically saying A is given by A plus something.
Correct. But this term is basically your future discounted reward.
What also means, is it for st plus 1 state?
Yeah, so g of t was given by this, right? So it will take all the future discounted reward.
No, I mean
What is
the
Minus what?
VST, and then you have the same variable on the other side too.
A equals
Yeah.
A plus.
No, here, on the first.
This one?
VFST, and
No,
on
And
this
the-
side also it's VFST.
Yeah, that's right.
Then the second term should be 0 immediately. Don't you think there is something?
Are you talking about this should be 0?
Oh, is this the updation step?
This is the
Oh,
updation
that's
step.
the updation step.
You're updating, so whenever you play it, you're updating, so say on the first time step, you have say some initial value that you have, say for example is 0, right? So this is 0 plus, this is your learning rate alpha, say it's 0.1, okay? This is the expected future reward that you have, which would be say, let's just say 1
Okay, I see.
minus 0.
Okay.
So this is how you update it.
Okay. Then what is ST?
ST is the current state. It's the value of the current state.
Value of current state?
Yeah.
Okay. Okay.
Okay. And similarly, you can do. So this is if you're doing it for the value function, you can do it for the Q function as well.
Can you give me a concrete example of the Monte Carlo one?
Of Monte Carlo. So say a very simple 3 observations and say just 2 actions.
Very good.
Initially say you're on state 1 with these 2, 1, 2, right? So this could be say, let's just give it 0, 1, say, okay?
So that is the Q table.
Alright,
Okay.
so
Then how we can get the V value function of V1?
the value for V1,
Yeah, V1.
okay, so let me just give you the example in terms of the Q function.
Yeah.
Okay? So in terms of the Q function, so say for example I'm in V1, I'm in state 1 and I go to state 2 by doing this action, the second action, right? So my initial value, so this is going to be 1, okay?
Why the initial value is 1? It's a VST.
Correct, because I'm taking action 2, right?
So you are taking action 2.
So this is my initial estimate of the current state that I'm in.
Current state or
Yeah.
reward?
Current state. So the reward, the estimate of the reward when I'm in state 1.
So basically that's reward. So the observation 1, 2, 3 is basically state 1, 2, 3,
Correct.
right?
Yeah.
And you are in a state V1. You are basically calculating
Yeah.
V1.
Correct.
So how calculate the V1 using that formula or the Q table, or how did you calculate the V1 given this table?
So since I said that I'm doing it for the Q value, right?
Mm-hmm.
For the Q value, you have S and the action A, right?
Mm-hmm.
So in this case, my S is going to be 1
Mm-hmm.
and my action I'm taking is 2.
2, yeah.
Okay?
Mm-hmm.
So that's why this value is going to be 1
Mm-hmm.
plus alpha, which is your learning rate. Okay.
So you are basically saying VST equals QSA.
Right, that's what I said. So there are two things that you can do. You can apply Monte Carlo temporal difference to the value function, and you can also apply it to the Q function. The example that I'm giving you is for the Q function. Let me make it simpler and update everything to the Q function.
So the Q value definition, QSA equals max A VS. So it will be great if you can write.
I'll write everything, yeah, in terms of the Q function.
Oh no. I think the definition can give me the clue how you transform the VST to QSA. Do I make sense?
I think he's asking how you derived the value of 1 from this max of VS.
So, yeah, 4. I'm sorry, I have a hard time understanding this. This is the first term we are calculating, right? So you use the, I was asking how you get this value,
Right.
and you said, oh, I use the QSA, right, to calculate this value. So this was the relationship between those two. So it's like a QSA equals max A VS. So it's the same. If we apply QSA, we got the VS. Do you see how we apply the formula?
Yeah, I see the confusion.
No. Yeah. So I think we are the mathematical definition here was used here. I was asking how you calculate the V, and you say you use the Q value, right? So it goes back to where I could not get it.
Right. I
So
got it.
So can you quickly check the internet or your resource
Sure.
to find how the Q value and V value relations are formed?
Yeah.
It's already surprising. There is some minor detail
Yes.
in the beginning. If I can understand it, at the end of the day, it comes back to where it catches you. So it's better to understand it correctly. Value function.
This is what is the V of S is max A of Q of S.
Yeah, so the formula was actually the opposite. So Aishwarya, understand it? correctly and try to explain on top.
Time switch.
Can you send me the link?
Sure.
Maybe in the Slack sender.
Yeah.
Ah, I found it, yeah.
Can you send it?
Either towards this data science.
No.
Send me the paper.
I'm not completely sure about this representation of Vs, but theoretically what it says is V of S, like you said, is the maximum reward possible for that state.
I can understand that.
Okay? Maximum reward. Now, so a state will have different actions, and a reward associated with different actions. Right. So now what Q of SA is saying is each of these reward associated with each action. So this is 0.3, 0.25 and so on, and 0.5. So the maximum reward that can be associated with this state is 0.5. Right? This is V of S. This is what I understood. And these values are Q of SA.
Then
That's what I understood from the theory. Do you have any inputs here?
Yeah, that is P of S.
So what it reads here is the optimal Q function, which is Q of SA, means the expected total reward received by an agent starting in S when it picks action A. So Q of SA is an indication for how good it is for an agent to pick action A while being in status, like you said.
So I think now I got the idea. So for the main thing broke here. So the reason why I had so difficult to understand was it should be Vs is max A Q S A.
Right.
Do you understand?
Yeah. I mixed it up. Yeah.
Yeah. Do you
So we're choosing the maximum value here as V of S.
Yeah,
is
so-
it like we start like the optimal V, not just any V.
optimal
V
B
is-
is already optimal. So V is like a
Okay.
maximum possible value.
Yes.
So it's already optimal.
Okay.
So let's say you have this kind of table, right? It's a very simple table. If you are this state, if you do this action,
The reward.
your expected reward is something. If you do this reward, your expected reward is this something. Then what will be the maximum possible reward you can achieve? Is you choose the action that has a maximum
Reward.
right?
Okay.
For
Yeah.
do I make sense?
Yeah.
So if we change this, I think it now I can go to I can understand up to how about we start again? So let's see how it goes.
Shut up. I don't know.
So let me use the Q value notation. So for Monte Carlo, you do the Q for a given state, and you're going to update it with plus alpha, so your learning rate, into in this case g of t, which is the discounted future rewards, minus the q of s comma a. Right?
So
So, can you
this one is
explain?
different from what you wrote earlier?
He just changed the
change
VS.
the notation to use the q value notation.
And can you explain how you those update term GT, is it GT or how do I read?
GT is what I wrote earlier is the expected discounted
Then how we can calculate GT?
So in Monte Carlo, what happens is you run the full episode first before you can make any update. So say for example, just 10 steps, right? You reach step 10 and you'll calculate for the last step first, okay? So then you have the value for the next step, right? You have the reward for all the steps up till then. So then you can update all the steps backwards up till the first step.
So, can you show me the last step? So you say you begin with the last step.
Yeah, so the last step will be 0.
So can you write it?
Sure.
So we have one state and 10 actions?
No, not necessarily.
No.
Just 10 states with, let's just say 2 actions. So you will first get the S of 10, okay? In this case, since it's a terminal state, right, this would become 0, okay? Then you go to S of 11 given whatever action at step 11, okay? So this will be the previous value.
So I thought you are going backward. Should it be S9?
Sorry, 9. My bad. Yeah. S9, okay, plus 0.1 into, in this case, you must have got some reward for reaching the terminal state, right? So if it was a positive reward, say for example, it's 10, because you won the game, okay, minus your initial value of at S9, okay? So say for example, this was very low, okay, and you've done something good because you won the game. This estimate will increase.
Okay. Can you use the three state 2 action table?
Okay, 3 states. Let me make this bigger. let's just say they're all
So we start with
0.5.
a random value, right?
yeah, all random. Let's just say one, say,
Mm-hmm.
minus 1, 2, say.
And to make things easier, let's say after 4th step, we got reward.
Okay, so you're saying the fourth step,
Yeah, so S1, S2, S3, S4.
and you're saying fourth is the terminal step, right?
Yeah, S4 is terminal step.
Okay. Yeah. So
Mm-hmm.
this case S4 would be 0
Why QS4A
Max.
is 0?
because once you've finished,
Mm-hmm.
right, there's nothing that you can do.
Mm-hmm.
Okay. It's the you've
So-
already finished the game,
The expected value is 0.
right?
Okay.
Okay.
Mhm.
At S3, okay, S3. So
But would we not be writing the actual reward that you got there? Because Q of SA is the actual reward plus the expected reward, right?
What? Q.
Like when
You're saying
after you
this?
reach the final state,
Yeah, after you reach the final state, for
Where-
reaching the final
Yeah.
state, you would get some reward plus the expected future reward. The future reward is obviously 0 because you reached the end
no,
of
so
the
that
game.
is for S3. So at S3, I'm gonna
You
take
get
an
the
action.
reward.
Say I'm gonna take action 1. Currently it's 2. Okay, and I get a reward of 10. Right. So this is 2.
Oh, that's the final reward. The final reward
Correct.
you get is at S3.
Is at S3.
Okay.
Final reward is S3.
When you take an action at S3, you will get a reward. So that's your final reward. Then there's no more steps after that.
Mm-hmm.
You've reached the terminal state.
So you do action, get reward. That is S3.
Right.
Mm-hmm.
So in this case, this becomes 10 minus 2, that's 8.
Mm-hmm.
Into 0.1, that's 0.8.
Mhm.
So it has increased to 2.8.
Okay. So.
If this was a bad state,
Mm-hmm.
so say for example it's minus 10, okay, this measure will reduce
Mm-hmm.
the value of taking action 2 at step 3.
Mm-hmm. Okay. I think I get the idea. Thank you. We are done for today. So
Okay.
Paul, can you pick very easy, concrete example?
I have a very easy example to write in code which will take 10 minutes.
Okay. Then, does it use the Monte Carlo method?
It uses temporal difference.
Temporal difference.
Which-
So then, can you explain
let me
temporal
explain.
difference?
So temporal difference
Mm-hmm.
is very similar to this.
Mhm.
The only difference is you do not want to wait till the end of the episode, especially for very, very long games.
Mhm.
If you keep waiting, obviously there's no update until then.
Mhm.
So instead of using the expected discounted future reward,
Mm-hmm.
you use the estimate.
Mm-hmm.
Okay, and so what that means is so you use the current reward that you get,
Mm-hmm.
okay, plus whatever is currently in your queue table
Mhm.
for the next action,
Mm-hmm.
okay, and here you use the max, okay. So what this means is
Mm-hmm.
you're starting at step 1, okay, suppose it's 0.5, okay,
What do
the
you
first
mean?
action, you're starting at step 1, okay,
State
yeah, state 1, let's say you take action 2,
State
Okay.
1,
Action two.
action 2.
right.
Okay.
So what you'll get over here is the current value
Mm-hmm.
is going to be 1,
Mm-hmm.
okay, plus
Mm-hmm.
in this case whatever reward you get. Suppose the reward is good, so say plus 10,
Mm-hmm.
okay, plus now you look at the next state 2, okay, and you take the best action possible from state 2.
So,
Yeah.
let's say at state 1,
Hmm.
I did action 2.
Yeah.
Then which state will I go? So there should be a separate table, or
No, there's no separate table. So you will apply that to your environment. Your
So-
environment will return a state.
so environment will return the state,
Correct.
right?
Yeah.
So at state 1, I took action 2, then environment returns with a reward and the next state.
Correct.
So I got the next state, which let's say is a 2.
Yeah.
And what is the A? Is a VS, so it's a maximum possible reward
Reward
for
that state.
So it
Correct.
will be 0.5.
Correct. Minus your initial value again.
Mm-hmm.
Right? So the difference here is that this is using your current estimate that's in your table.
Mm-hmm.
Whereas,
Can I interrupt you? Can you explain again how you got 0.5? In the
so basically, you are at state 1, okay?
Okay.
You are taking the best possible action that you can take over here. So you've chosen action 2,
Okay.
right? Now, what you want to do is, this will get sent to your environment, right? Your environment will return a reward and the new state. This state could be 2, it could be 3, it could be even 4. Okay? So if it is 2, right? Then you basically want to compare that with the best possible action that you can take from state 2. So say for example you have 2 actions, this is very bad, this is very good. But you know that you have a possible good action, right? Suppose this was also bad. Then what would you take? You will still take this because this is still lower than that, and this estimate will now reduce because you're going from a good state to a bad state.
Okay.
Yeah. But in theory, like, what are we trying to accomplish with temporal difference?
The difference here is that you can update this at each time step. You don't have to wait till the end of the episode.
Okay.
Each change of state, you get a better approximation.
Right.
Better estimate.
Yeah. And another thing is, Monte Carlo cannot be used in continuous actions. Continuous environments are when it never stops. Say for example, like stock exchange and things like that. Right. Okay.
Okay, very good.
So should we start?
The values in the table is actually a reward. What are these?
Yeah,
values?
it's your expected reward
Okay.
given a state and an action.
So that expected reward is the reward for that state plus the expected future reward.
Yes, because it's the expected future reward. Yeah.
So we can say the goal of the reinforced learning is getting the Q table.
This
Right,
is
or
this is
right
one
or
kind. This is just one kind
So
of
it's
algorithm.
the Q learning.
Q learn. Yeah.
So the goal of the Q learning is learning the Q table.
Right.
Okay.
Okay. Okay, so I'm starting. You can follow along. Just some imports, and then we're going to use the OpenAI Gym interface. So basically, it's just an interface to interact with different environments, and there are a set of functions that you can use to pass an action and retrieve the reward and the next state, whether it's a terminal state and some extra information. So what we'll do is environment.
Could you zoom in a little?
Yep, sure. You always have to call environment or reset. Okay, and then okay, so this is a simple smart taxi game. The yellow figure is where the taxi is. These lines are walls. so you'll get a negative penalty of -10 if you try and go into a wall. The blue value is where you have to pick up a passenger, and the purple value is where you have to drop him off. Okay, there are only 4 possible pick up and drop off destinations, and you basically get a reward for dropping them off correctly.
What is GFB?
So these 4 places are the 4 possible pick up and drop off spots. These could be highlighted because those 4 places can change. So say for example, if I run this again, it will create a new thing. Now this is the pickup, that is the drop off.
Okay, so
B is the pickup, G is the drop off.
In this case, blue means pickup, purple means drop off.
And the yellow thing is the taxi.
Sorry?
And the yellow thing.
The yellow is the cab, where the cab is currently.
And the R and the Y?
It's just
name
2
of
different
the name
yeah.
of the place.
Yeah, name.
Yeah.
Okay. So quickly, what we'll do is we'll see how long it takes to do random sampling to finish this off. Okay.
So what happens if we hit the wall?
You get a negative penalty of -10, and the state doesn't change.
Okay.
Okay.
So what are the actions of taxi?
Yeah, I'll show you that. One second. That's a good question. So, in order to see the possible actions, what you can do is print env dot action space dot n and observation. Okay, so basically it says you have 6 possible actions. The actions are to move left, right, up, down, pick up and drop off. Okay, and you have 500 possible states. Why? Because it's a 5x5 grid, so it's 5 into 5 into 4, because there are 4 possible destination locations, and into 5 again for places where the passenger is. So the passenger could be at any 4 of the source places, or he could be inside the cab, so that becomes 5. So your total possible state space is 500.
So you have to pick up and drop off as a command.
Correct.
Okay.
Okay. Okay, so it's going to sample random actions.
What did you do while if reward equals to -10? Or what is the logic there? Why?
So you get a reward from the environment.
Crash.
I just want to check how many times he's crashing into a wall.
So reward should be 10 or -10?
-10 when he crashes into a wall. So I'm just counting the number of penalties that he's incurred.
So if we hit the wall, we got 10-point penalty,
Yeah.
and this penalty is like a time penalty.
Yeah,
You-
basically
you-
towards your final score.
Yeah, so you are
Yes.
creating a new time-based penalty.
Okay. What happened here? Oh, sorry.
What if
One change I need to make. So I basically sampled an action, and then in order to use the action, you do env dot step. Okay. Okay.
How about adding, if we got minus 10 reward by hitting a wall, how about adding this negative reward to the penalty?
I mean, that doesn't really matter because here, this is just a visualization of when you're doing random samples, how many penalties is incurring. It doesn't, like, the actual penalty doesn't really matter right now when I'm visualizing it.
So
it basically means to say I've hit the wall 1000 times.
you hit the wall 1000 times?
Yeah. So whenever
I see,
Right?
I see.
So with a random sample, this is how long it actually takes to finally drop off one single passenger. Okay. So now let's create a Q learning agent. So you first create a Q table. So you have.
Is it possible to go through this code again, like what it is doing?
This code?
Yeah.
So basically,
Line.
you initially just set a variable done to false because done signifies whether you've reached a terminal state or not. Okay. You first reset the environment because every time you want to play a new game, you want to reset the environment. Okay. So then I just initialize penalties and steps both to 0. Okay. So before starting, you have 0 penalties, you have 0 steps. Okay. So now I have a while loop. So while not done, okay, I'm going to keep sampling random actions. Okay. So your action space is the 6 possible actions. It will keep sampling, so you will get an integer between 0 to 5. Okay. And then you do environment.step. Okay, with that action that you sample. And so this is the gym interface. It will return these 4 things. Okay. So the state is your next state, your reward, whether it was a terminal state, and some extra info, and that is only for debugging purposes. Generally, you cannot train your agent with it. Okay. Then I'm just checking if the reward was a -10, that means he crashed into a wall. Okay. And I've added the penalties, incremented by 1, and at every step I incremented the step at 1. That's it.
So
Okay.
basically, so whenever it says total penalty is 142, so does it mean that it will?
142 times it crashed.
Yeah.
Into the wall.
Okay.
Okay, that's.
So So I've created a simple Q table with initialize everything to 0.
Is it okay to initialize everything as a 0?
Yeah. Okay. Now what we need to do is we need to.
Can you show the code again?
Can you write how we get the 500 observation space?
What's the
component of the?
So your grid is 5 by 5.
5 by 5.
So you have 25 possible locations for the taxi. You have 4 destinations. So that's 4. And the passenger could be at 4 source locations.
3? Is it 4?
4.
Or
It's possible states. It's not necessarily that.
Is it possible the pick-up location and destination is same?
No, but the thing is, say for example, you had those 4 destinations, right? Okay. At one point, this. How do I explain that? Okay, so let me say it this way. In game 1, the location 1 could be a destination, but in game 2, the location 1 could be a source,
Okay.
right? So it's two different states. At the same time, they cannot be both, but in two different games, it could be.
So it's a basically, let's say it's a 4. Continue. Yeah.
Yeah, so 4 for source plus if he's inside the taxi. So plus 1.
Inside the taxi?
Yeah, so he's already picked him up.
Oh, is that possible? What do you mean by?
So say for example you start the game, the taxi moves to the source location, picks up the customer, okay, and then he moves, right?
Okay, so let's say, okay.
So that's plus 1, so that's 5. So it's going to be 5 into 5 into 4 into 5.
Okay.
I mean, the customer could be one of the 25 different cells. And the customer,
What was
No,
the
no,
it
question?
could be, the customer is always on the source
Why is
location.
there 500?
There are 4 possible sources.
Why is the overall action space 500?
Okay, let's continue.
Okay. So okay.
Paul?
Yeah.
Okay, is it the number of word random?
Number?
Word. Word is always same.
No. It's random.
Are you sure the word is random?
Yeah, if you keep running environment.reset, it will create a new.
I am doing it.
The wall is the same.
You're saying the walls?
Yeah.
Yeah,
the wall.
I'm.
Oh, the walls.
Yeah, I'm.
Yeah, but that doesn't matter, right? That's not being considered in your state space.
Let's say if we remove the 5 words, because the text cannot be at the word.
No, but the wall is not part in of the location. So the taxi could be this side, he could be this side.
So the penalty is if you move from left of the wall to the
Correct.
right or right of the wall. to the
So, how many locations the text can be?
25.
25?
Yeah.
Are you sure?
Yeah.
So text can be
1, 2, 3, 4, 5.
1, 2, 3.
No, he can
it
go on to this
go
side.
on the.
He can go on to the
location.
destination or source locations.
1, 2, 3, 4, 5,
Yeah.
right?
Yeah.
Okay, I see.
Okay, and another thing is we're going to be using greedy epsilon, which is an algorithm that it's a very simple algorithm for the exploitation problem. You basically set epsilon to a small number. Okay, so say it's 0.1. Okay, so then you get a random number generator, get a random number. If it's less than epsilon, then you'll do a random sample. So he'll explore. Okay, if it's anything else, he'll exploit. Okay, so when I say exploit means you'll look up the Q table to take an action. When I say explore, he will take a random sample. Okay, so let's say alpha is also 0.1, let's say 0.6. Okay.
What is gamma?
Your discount factor.
Where does the discount factor plays role?
Where do I write that? I didn't write it. Oh, I'm sorry. It should be here.
Okay.
Okay. So I'm taking the argmax would give you the index of the maximum value for that row. Okay, and now what I need to do is I need to calculate my the Q values. So Q old is equal to okay. Q old plus
I think you missed the multiply between alpha and parentheses.
yep. And one thing here, change the state to new state because you still need the old state at this point. Okay. Does that make sense?
Is it
Okay.
new state? Q
Yeah,
table.
new state.
Can you make the font a little smaller? Oh, okay. Sanas, try come closer.
So you need to update Q table.
Yeah. Oh, yeah, you're right. So Okay, so now the Q table has been updated.
Can I sort the code? Just a second.
Okay, and now what I'm going to do is I'm just going to modify this to save some time. Okay, so we don't want to create this loop again. You want to, instead of doing a random sample over here, you want to look up your Q table for the current state. Okay. So if you see, now he's got 0 penalties and he's finished it in 15 steps.
Can you go to the code?
Of that code.
What is the other place we have defined Q table?
Should be just above this.
I don't know why it's on that. Because on that line maybe 16. Q table state action first of I don't know, I'm getting either syntax error when
Right?
Q table state action equals to Q.
What's the error?
No, it's invalid syntax. The down one where before state equals to new state. So I'm trying to figure out.
This one?
Yeah,
Can you show me how you define your Q table?
like Q table equals to numpy dot zeros in observations. Exactly.
But do you have 2 opening brackets?
Yeah. I don't have errors on that one, but most.
This is Q state
It's not
action.
showing now.
Oh, it'll take time to run it on the server itself.
Okay.
This way it is done. Pronounced. It is
I'll check it.
Yeah. State action.
This is np.argmax of Q table and Q table of state type.
Right. Correct.
How long do you think it will take on this?
Shouldn't be too long, but
Straight to the sun,
did it work?
Maybe if it takes long time, you can range the number of times you're iterating. He gives 10,000, you can give maybe 1,000.
Okay.
Good.
Can you send the code?
Yeah. The last pattern.
It's okay?
This one.
So this is strange. So the first time it finished train, and when I run it run infinitely. So I stopped it and just run again. This time it finished in 10 steps. So
Oh, that's
very funny, yeah.
For me, it always done.
Yeah. But yeah, I think there was a very edgy case. Somehow it created infinite loop. The Q
Because it's why
create-
not done.
Yeah, Q-table created an infinite loop. So in 10,000 steps, he could not finish the training, and there were
Yeah.
infinite loop there.
So one way is normally you can set a limit of 200. So the old gym APIs, right? So if you don't do .env, okay, it will now use the new version.
Mm-hmm.
And in this case, there will be a maximum of 200 steps that you can take. So if you, even if I do random something here.
Okay, great. Please, thank you for doing wonderful seminar. It is really difficult to do this level of seminar. So good job, Paul.
Thank you.
See you next week.
So next week we'll do